We're going to begin our study of relations by looking at a familiar type of relation as a kind of warm-up, what we call a linear relation. The goal here is to illustrate our theme of multiple representations of relations. Recall the two central themes of precalculus that we introduced in the last lesson. There was the idea of relations between multiple quantities, usually two quantities for our purposes, and the idea of multiple representations of those relations. That is, the same relation can be represented either numerically, graphically, or analytically. And again, we'll get acquainted with these a little bit more closely by reviewing something that you already know from your study of algebra, what you know about linear relations. You might not have seen that phrase linear relation before, but you have studied these kinds of relations, maybe using slightly different vocabulary, which we will recall in just a moment. So we'll take a look at linear relations, and we will eventually turn to and concentrate on a particular property of these, what is called the slope, and how to represent these analytically using linear equations. Let's begin by looking at how to recognize linear relations when we encounter them. We can define a linear relation, and we'll do this by using a graphical definition. We'll say that a relation between two variables or two quantities is linear if the graph of that relation, that is a graphical representation of it, is a straight line. Now, there's some vocabulary in this definition that we haven't yet really defined or said much about. There's the word relation, which we still haven't defined, and there's also this phrase graph of the relation, which we also haven't really defined, although I'm relying here on you at least having some sense of what these things mean. We will give more precise definitions of these soon, but for now, trust your intuitive understanding of them as best you can. And if anything's unclear, it will become clearer as we look at some examples. Now, again, notice that our definition here is a graphical one. We're defining a linear relation by referring to, in this case, the shape of its graph. We could try to give a purely numerical definition of a linear relation. It would be a little more difficult. Actually, it'd be much more difficult for a variety of reasons related to the limited character of numerical representations. This is going to come up a lot. We're going to see this quite a bit when we're characterizing different types of relations. We will often emphasize graphical and analytical representations rather than numerical ones, just because graphical and analytical representations are much more flexible and much more general. They can apply to lots of relations of the same type. But let's see how we can relate numerical and graphical information. So let's look at a graphical representation of a linear relation between two quantities, which we'll call x and y. Here is the graph, and here's a question. We want to know what y is when x is equal to 0. Now, I'm presupposing here a little bit of familiarity with how to read the kind of picture we see here, but if you know that from your algebra courses, you should be able to answer this question. You should be able to see from the graph that when x is equal to 0, y is equal to -1. Another question we could ask is this. Say we want to know whether y is greater than or less than 0 when x is equal to 1. Well, again, by looking at the graph, you should be able to figure out that y is less than 0. And if you don't see why that is in the graph, we'll look more closely at how to interpret all of this soon. But the key thing to note right here is that we are drawing numerical information about particular numerical values of, in this case, y, based on information we see in the graph. This is an example of how we can take a graphical representation of a relation and, in a sense, translate it into a numerical representation, or at least numerical information about the relation. Let's turn now to the third kind of representation that we have, analytical representations. Now, here, a lot depends on the type of relation we're working with. So if you're translating between a graphical and an analytical representation of a relation, it often helps to know something about the type of relation you're dealing with. And that's going to be a lot of what we study in this course, how to classify relations into types and to recognize those based on both graphical and analytical representations. The good news is that for linear relations, this is pretty simple. One thing we can say here is that a line is fully determined by any 2 points on it. What this means, that phrase fully determined, means that if you know 2 points on the line, if you know where they are, you can figure out anything else that you want to know about the line on the basis of that initial information. So knowing 2 points on the line is enough to know, with a little bit of work, everything there is to know about the line. The reason why, or one part of the reason why this is the case, why 2 points are enough for a line, is because, as you already know, any 2 points on a straight line are connected to each other in a sense by what we call the slope of the line. So let's recall how slopes work and how they can be used to come up with linear equations, which are analytical representations of linear relations. Again, this should be review, but we'll go through it just to make sure you remember how it works. So you can think of a slope of a line as a numerical representation. It's a number, but what it tells us when we're thinking about the line is the direction in which the line moves. And we can find this slope, this number, by finding a ratio. We find the vertical distance we move when we're going between 2 points on the line. We sometimes call that the rise. And we divide it by the horizontal distance that we travel when going between the same 2 points. We sometimes call that the run. So here's a kind of diagram to illustrate this. We've got our line in blue. That's our linear relation or our graphical representation of it. We have 2 points on it. We'll call them P and Q for now. And if we move from one to the other, say from P to Q, we travel a certain horizontal distance. That's the run that you see there. It's the length of that horizontal line segment. And we travel a certain vertical distance, labeled here as the rise. Now, we often use the letter M to denote the slope of a line, and we can come up with a kind of formula for the slope. It's rise over run. So calculate the rise, get a number for that, and divide it by the run. Another way to write this, which you see sometimes, is delta y over delta x, where the delta here is a shorthand for basically the change in the value of that variable. So change in y over change in x. Or if you want an algebraic expression for this that tells you how to calculate it, here it is. y2 minus y1 over x2 minus x1. So here we're using the x and y coordinates of the 2 points in order to calculate the slope. And if we know what those coordinates are, we can plug them in there and calculate the slope. Let's take a look at an example. Say that we have a line and we know that these 2 points are on the line. We're going to refer to them using their ordered pairs. We have the point 1, 2 and the point 5, negative 3. Our goal is to find the slope of the line. Well, we'll use the slope formula. There it is. The slope m is equal to y2 minus y1 over x2 minus x1. So for y2 and y1, I'm going to plug in the coordinates, the y coordinates of our 2 points. These are the second numbers that appear in each of those ordered pairs. So I'll use negative 3 for y2 and 2 for y1. And then for the x values, x2 and x1, we'll plug in the corresponding x coordinates. Notice that 5 goes first because x2 here is paired up with y2. So we have 5 minus 1. At this point, the only other work is arithmetic. Just do a few calculations. you end up with -5/4, -5/4. That is the slope of our line. Now let's find an equation for our line. So we're now going to find an equation, or what we could also call an analytical representation of the same line, the line that contains the points 1, 2, and 5, -3. We already know the slope. We just found that. We found that the slope of this line is -5/4. So pick a point on the line, call it xy. Let's say that's a point on the line. Whatever point we choose, whatever x and y values we have for a point on the line, if we calculate the slope of our line using this point and one of the points we're already given, we need to get -5/4. In other words, we can plug these things into the slope formula, -5/4 for the slope, y for y2, x for x2, and then I'm going to use 2 and 1 for y1 and x1. Plugging all that in gives us an equation with x and y as the variables. Now, this equation is an equation for our line. It does everything we want. If you pick values for x and y that solve this equation, that make it true, it will give us the coordinates of a point on our line. And every point on the line can be thought of as, in a sense, represented by this equation. Now, you might look at that equation, I'll put it back up on the screen once more. You might look at that equation and say, wait a minute, that's not how we write linear equations. Well, in a sense, you're right, although let me emphasize, there's nothing wrong with the equation we've written here. It's a perfectly good equation, and it does the job we want. It represents our linear relation. But given a relation, there are almost always multiple analytical representations of it, multiple equations for it. So the equation we got just a moment ago is an analytical representation of our linear relation. There's the equation once more. It's not in a form we often use for linear equations, but again, that's okay. It does the job. Any equation that is, we say, equivalent to this, equivalent in an algebraic sense, will also do the job. It will also represent our relation analytically. So if you want, you can rewrite this equation into an equivalent form by doing some algebra. And it's fairly common, as you know, to identify certain standard forms for these things. That is, certain standard analytical representation forms for different kinds of relations. Again, though, I'll emphasize, these are for convenience. It's not as though there's only one correct way to represent a relation analytically. There's just some that are a little more familiar and a little more standard because it makes things easier to talk about. Let's look at some of those common linear equation forms. One that is especially useful, especially in calculus, is called point slope form. It's usually written like this: y minus y1 equals m times x minus x1. Here, there are several letters that appear in the equation form. Some of them are variables, some are more like constants. So when you're finding an equation for a particular linear relation, x1 and y1 here will be filled in with the coordinates of a point you know is on the line. So x1, y1 is an ordered pair for some point on the line. Any point will do. M, as usual, is the slope. Notice here, by the way, graphical features of our line are appearing, in a sense, in the equation. The slope, which is really a graphical thing, it's something about the direction of the line, is there in the equation, in the m place. The coordinates of a point on the line are sitting there in the x1 and y1 places. So this is how, again, graphical and analytical relations or representations of relations can be sort of weaved together. So that's one common linear equation form. Another one that you've probably seen is called slope-intercept form. We usually write it like this: y equals mx plus b. Here again, m is the slope of the line. B is what we call the y-intercept of the line, the value of y when x is equal to 0. It's worth noting, by the way, that you can get slope-intercept form from point-slope form. If the point you know is on the line, the point x1, y1, if that is the y-intercept of your line, then slope-intercept form and point-slope form look pretty much exactly alike. Point-slope form is just a little more general because it allows you to work with any point on the line. It doesn't have to be the y-intercept. So let's look at an example of how to use these. Say I tell you this information about a line. It has a slope of 4, and the point 1, 2 is on it. We want an equation for this line. Well, notice the information we're given. We're given the slope of our line, and we're given the coordinates of a point on our line. This sets us up to be able to use point-slope form very easily. There's point-slope form once again: y minus y1 equals m times x minus x1. Here, the value of m is going to be 4. That's the slope of our line. We're told that's 4, so m will be equal to 4. And we're given the coordinates of a point on our line. It's the point 1, 2. So x1 here will be equal to 1, and y1 will be equal to 2. Let's plug those into our equation form. This is what we get. Y minus 2 equals 4 times x minus 1. There's an equation for our line. Let's build on this example a little more. Let's say we now want to find the y-intercept of our line. So we're talking about the same line as before. It has a slope of 4. It goes through the point 1, 2. Now we want to find its y-intercept. Well, we already found an equation for the line. There it is. Y minus 2 equals 4 times x minus 1. If you want to find the y-intercept now, there are a few different ways to do it. One of them is to do a little bit of algebra in order to rewrite our equation so that it is in slope-intercept form. So let's do that. We want to take the equation that we currently have, and we want to rewrite it in this form: y equals mx plus b. So there's our equation. And now we're going to distribute the 4 on the right. So on the right side, we get 4x minus 4. I'm now going to add 2 to both sides of the equation. And our equation turns into this: y equals 4x minus 2. This equation represents exactly the same relation as the one that appears above it. But it's in a different form. It's in slope-intercept form now. And the number in the b place is -2. Remember that minus sign is going to stick to the 2 and make it -2 here. So we can conclude that our y-intercept is the point 0, -2. Every y-intercept has an x-coordinate of 0, and we just found that the y-coordinate is -2. So there's some more graphical information that we are getting out of the equation. I want to return to something we discussed a moment ago, the idea of different linear equation forms and the idea that one of these might be correct or incorrect in some sense, especially in your earlier algebra courses that you've taken. It's very likely that your teacher put a lot of emphasis on slope-intercept form. You might have even been told at some point along there that if you're solving a problem involving a linear equation, the only, so to speak, right answer is the one in slope-intercept form. Well, this is to make things easier for your teacher. The reason is because any given line has only one correct slope-intercept equation for the most part. There are certain exceptions, but we won't worry about those. So it's a lot easier for your teacher to grade your work if you're putting your equations into slope-intercept form, because there's only going to be one correct way to do that. But our goal in pre-calculus is to get you ready for calculus. And in calculus, turns out that point slope form is often a lot more useful and a lot easier to use. And so we will often emphasize point slope form when writing linear equations here in Precalculus. That way you'll get used to using it. And again, this is all part of our central theme of understanding multiple representations of a relation. Not only can the same relation be represented in different ways, numerically, graphically, and analytically, but the same relation can be represented by multiple different analytical representations, multiple different equations. And it's a mistake to say that any one of them is the correct representation or the correct equation for the relation. They all do the same thing. They all represent the same relation. Which one we want to use really just depends on what's easiest for us, what's going to take the least amount of time and lead to the fewest mistakes and so on. So we'll often want to think here about our goals in writing an equation, as well as the information that we have available as a kind of guide for what type of equation form is best to use in a given context.